Good morning, everyone. My name is Han Yu. I'm from Alibaba, and apparently my name is not among the authors. That's because I'm here to present this work on behalf of the first author, Wei, who cannot be here due to some visa issues. Okay, let's get started. This work is about rethinking key-value cache compression for LLM inference serving. This work is a joint effort from Nanyang Technological University, S-Lab, and Shanghai AI Lab. Oh, by the way, I am not quite familiar with this work, actually, so I might not be able to take questions after the talk. And if anyone has questions, just send an email to the author. I will show their email address in the final slide. Sorry for this. Okay, in this talk, we are going to look into how we can make LLMs more efficient and cost-effective with special focus on the key-value cache compression techniques. As LLMs keep getting bigger, it's really important to find ways to serve them efficiently. So key cache is a big issue when it comes to serving LLMs. Let me give you an example. If we want to serve a Llama 3 70B model using FP16 format with a batch size of 512 and a prompt length of 2048, we need 130 gigabytes just for the model weights. And we also need an additional 512 gigabytes for the KV cache. That's a huge amount of memory. This shows just how important it is to reduce the memory footprint of KV caches. There are two main ways to compress KV caches. The first is quantization, which involves converting the KV cache into a low-precision format to save GPU memory. The second is sparsity, which moves less important parts of the KV cache from fast memory to slower memory, or just removes them. Substantial research efforts have been devoted into these directions. Even though there are many compression algorithms out there, we're not quite sure how well they work in real production environments. This paper looks at a bunch of existing algorithms and benchmark studies regarding KV cache compression and tries to figure out what's preventing them from being widely used in production environments. To this end, we have checked out over 40 papers and benchmarks looking at both quantization and sparsity-based methods. Interested readers can refer to our paper for more details of these surveyed papers. Next, we'll provide several qualitative observations derived from the literature review. We first discuss some findings regarding quantization-based KV cache compression techniques. First, we find that while finer quantization can keep accuracy high, however, it typically introduces irregular computational pattern, thereby limiting the effective utilization of GPU resources. Second, some research efforts attempt to introduce extra step to mitigate the quantization outliers. This operation incurs more GPU memory consumption and computational overhead, potentially offsetting the computational efficiency gains brought by KV cache compression. And third, most quantization-based algorithms keep a window of recent historical KV cache as full precision for accuracy considerations, which could burden the compatibility with paged attention. The window-based quantization demands two types of paged tensors to manage full precision and quantized KV cache, respectively. This introduces unstructured computation patterns when computing the attention outputs. This design increases the deployment complexity, degrading the computational efficiency. Here we discuss sparsity-based KV cache compression techniques. First, we investigate the granularity of KV cache compression, including token level, layer level, head level, and channel level. Similar to quantization-based techniques, pursuing finer granularity in sparsity-based methods can yield improved accuracy at the cost of high computational overhead due to the irregular computational patterns. Second, many studies do not consider important serving techniques like flash attention and page attention when measuring throughput. The integration of sparsity-based methods with flash attention and page attention might increase the implementation complexity and undermine the potential computational efficiency advantages, highlighting the necessity of dedicated systematical optimizations. We also analyzed the evaluation settings of the collected KV cache compression works and summarized the following findings. First, many compression studies used transformers library to measure the throughput, and they often leave out some LLM acceleration techniques like flash attention or page attention. Second, they do not pay much attention to how compression affects response lengths, which is important for end-to-end latency performance. Third, long context tasks are challenging for KV cache compression algorithms to maintain the accuracy. Many works report the overall performance, but they often overlooked the analysis of response quality for individual samples. So based on the qualitative discussion from literature review, we desire to perform quantitative analysis in throughput, length distributions, and negative samples to investigate the efficiency of existing KV cache compression techniques. Here we show our evaluation setup. We use the frameworks including the transformers library and LLM deploy. We chose LLM deploy for evaluation because it is easy to modify to support various KV cache compression techniques with flash attention and page attention. As for LLMs, we considered Llama and Mixtral on datasets including Shared GPT and Longbench. We use Shared GPT to perform length distribution analysis and Longbench to conduct negative samples analysis. As for compression algorithms, we considered quantization-based techniques including KV and GEAR, sparsity-based approaches including H2O and streaming LLM. We first utilized synthesized samples and Llama 7B to analyze the prefill and decoding throughput of LLM serving acceleration techniques. In figure A and B, page attention and flash attention can improve the decoding throughput. Figures C and D show that the relative speed up on the transformers library does not show a significant advantage when measured against page attention and flash attention. This suggests that the computational efficiency results on TRL are not reliable if we want to deploy it in production environments. We should measure the throughput using established LLM serving frameworks with prominent techniques including page attention and flash attention. In the second row and third row, we measure various KV cache compression techniques over different batch sizes and KV cache lengths. We observed that KV cache compression methods show negative computational efficiency in certain scenarios of batch sizes, sequence lengths in the prefill and decoding stage. Based on our throughput performance measurement, it is recommended to apply compression algorithms for serving requests with heavy KV caches. Then we analyze the impact of different KV cache compression techniques on response lengths. In this figure, we compare the response lengths between the FP16 baseline and KV cache compression techniques. Our observation is that lossy compression tends to make response length variation much bigger, and this gets worse with higher compression ratios. The lengthy responses might lead to longer end-to-end latencies, which outweighs the benefits of high throughput brought by the KV cache compression. And then we present the distribution of end-to-end latencies of different KV cache compression techniques. Specifically, we measure the latency for each sample in the Shared GPT dataset with a fixed batch size of 1. We noticed that the performance gains of compression methods are not significant because KV cache compression might reduce the throughput and increase the response lengths. Finally, for the negative sample analysis, We define the negative samples as benign samples where KV cache compression causes relative accuracy loss beyond a set threshold. In this figure, we vary the threshold and collect the numbers of negative samples for different KV cache compression techniques. We find that the KV cache compression algorithms naturally produce negative samples. The algorithm with higher accuracy can reduce their occurrence, but it is challenging to eliminate them entirely. In the left bar chart, we set the threshold as 10% and investigate the proportion of negative samples over task types. We observe that these KV cache compression algorithms struggle with specific tasks like summarization and question answering, because these tasks strongly rely on the accurate context information. Well, we summarize several limitations. Okay, I'll brief them due to the time limit. 3 aspects: throughput, length distribution, and negative samples. We will introduce several simple tools to tackle these limitations. The first one is the throughput predictor. We notice that KV cache compression only impacts on the attention throughput, so we profile it to predict the prefill and decoding throughput across different batch sizes and KV cache lengths. Second, we trained a length predictor. We collect the response lengths from different KV cache compression algorithms and use a BERT-based classifier to predict output length ranges. This shows the accuracy of the predictor, and you can refer to the paper for details. Another tool is the negative sample evaluator. We established a 10% threshold to detect negative samples and incorporated them into a benchmark as our conductive negative sample evaluator. This table shows the measured scores of various algorithms on this benchmark. The empirical results show significant drops across different task types, particularly in summarization and question answering. This stressed the importance of developing more robust solutions to enhance accuracy and reliability on these specific task types. This is a showcase of using the tools in request routing in serving. I will skip this, and you can refer to the paper. To wrap up, our paper gives a thorough review and empirical analysis of KV cache compression and figure out underexplored aspects of existing KV cache compression algorithms. We suggest evaluating the compression algorithms in 3 aspects, in 3 important areas: throughput, length distributions, and negative samples. And the tools we've provided are designed to make it effective to use these algorithms in production environments. And you may scan the QR code to access the open source codes, and you can drop an email to the authors for any further questions. That's all. Thanks for listening.